Good morning, everybody. I hope that the ionic bonding quiz wasn't too stressful a way to start your Friday. As I mentioned on block day, whether it was Wednesday or Thursday, depending on what class you're listening to, I have a meeting this morning, so I'm not able to be here for your class, but I wanted to get us started on the next part of the bonding unit, and that deals with covalent bonding. We'll see here at the beginning that covalent bonding and ionic bonding definitely have some similarities, especially in the reason why atoms form bonds and what they accomplish out of forming bonds, but there's definitely a difference in the way that they form those bonds and the way that they go about achieving the ultimate outcome of bonding. So if you haven't done so already, things you're going to need for today. First, you're going to need your something to write with. Second, you're going to need a periodic table. Third, you're going to need your introduction to covalent bonding outline. On Monday, when we started taking notes on ionic bonding, I gave you a big packet. It was 3 pages long. The ionic bonding notes take up the first 3 sides of that packet. The covalent bonding notes take up the last 3 sides of that packet. So, if you have that out already from the quiz, you're all good. If not, pull out that packet. So let's get those things together, and we will get started in just a few minutes. First, just to keep up with consistency, right, here's your calendar. I know it's pretty small and you probably can't see it, so I'll zoom in onto some things. First thing for today, you guys took your ionic bonding quiz at the beginning. Today, during class, we're going to get into the introduction to covalent bonding. So that's where we're going to start off today. Right now, there isn't any homework listed for this evening, for this weekend, but I'm probably going to update that later in the day. So check back later on today or sometime this weekend. Just a couple of pages from the book, or a couple of questions from the book, making sure that you're getting the gist of covalent bonding and the introductory part. On Monday, we will continue on with covalent bonding and talk about some of the ways that even though we classify stuff as a covalent bond, there are some ways that they are different from one another. Certain covalent bonds are different than other covalent bonds, and we'll talk about why that is on Monday. We'll talk about electronegativity, polarity, and how that leads to nonpolar and polar bonds. On Tuesday, I have covalent names or compound formulas and names. Names and formulas for covalent bonds are a little bit simpler than ionic bonds, basically because the formula is going to be given to you pretty much every time anyway, and we'll talk about that as we go along. And then we'll talk about the names. The names are a little bit more complex than ionic bonds, but still pretty okay. I still have quiz here for Tuesday. I'm thinking I'm probably going to move that quiz to the block day next week, so beginning of block day. I'll update the calendar and reflect that as we go along. Then, for block day next week, we are back on lab, but before we get to lab, we have to talk about some properties of compounds, and then we'll do the comparing ionic and covalent compounds lab. The comparing ionic and covalent compounds lab is pretty short. We should have no problem getting that in the last part of our block day next week, and that's our plan for block day. Then, on Friday, right now, I have us doing a comparison, basically, similarities and differences between ionic bonds and covalent bonds, and talk about, really get into the gist of how are they the same, how are they different, what kind of similarities they have, what kind of differences do they have, which is basically just saying the same thing I just said, and, go from there. So, right now, I still have the test listed for, oh no, stand by. Don't worry, if I don't make an actual square to zoom in, it's disappearing ink, so it goes away. Then I still have the test listed for Monday, December 10th. We'll see how that goes. We'll see how the rest of the next week goes, see if we need to adjust that date. So that's the calendar. But today, we wanted to get started on chemical bonding, but specifically covalent bonding. And as you can see here, it says electron sharing underneath. All right? So, starting off, when we talk about chemical bonding, sorry, I'm having some computer issues. I know that's shocking to all of you that I would have computer issues, but hopefully it will start responding for me. Stand by. Stand by. Chemical bonds. All right. This slide is going to look very similar to the first slide when we were dealing with ionic bonding as well. Because, like I kind of mentioned before, sorry everybody, computer's going a little crazy right now. As I mentioned before, there are a lot of similarities in bonding, just different ways we go about it. So first, a chemical bond is defined as an attractive force that holds atoms together. I hope that sounds familiar from what we've done up until this point. I think we reviewed it on Tuesday and block day. And we discussed that the formation of chemical bonds involves energy because, as we've discussed, energy is the ability to do stuff. One way or another, we'll kind of see, and I think I mentioned this sort of, is that one way or another, pretty much anything that happens out there can be related back to energy some way. More specifically, bonds will form between atoms if they have a lower energy together than when they are separated. Hopefully this all sounds familiar. The first Roman numeral on the covalent bonding packet is exactly the same as the ionic bonding packet because the ultimate goal is the same. Bond formation is generally an exothermic process. And we discussed when we were talking about ionic bonds that exothermic means that it's giving off energy. The products have less energy than the substances that we started with. That's what exothermic means. That means those things have become more stable. And finally, chemical bonding, whether we talk about ionic or covalent, deals with valence electrons, electrons in the highest energy level. That's still the case with covalent bonds, just like it was with ionic bonds. But what happens with those valence electrons is how we differentiate and make ionic bonding and covalent bonding different. So, ionic bonding deals with electrons being transferred between atoms. And hopefully by now you've gotten to the point where you realize that electrons are being transferred from metals to nonmetals. Because metals are looking to lose valence electrons, nonmetals are looking to gain valence electrons. So electrons are transferred between a metal and a nonmetal. Metal forms the cation, positive charge, because it has lost electrons. Nonmetal forms the anion with a negative charge because it has gained electrons. So ionic bonds occur between metals and nonmetals. But we'll find out that covalent bonding deals with electrons being shared between atoms. One of the requirements for electrons to be shared is that both of the parties, really the requirement for anything to be shared, is that both of the people or the things involved want the same thing. There has to be that desire for electrons between both atoms, which means we've already established that nonmetals are looking to gain electrons. So covalent bonds occur between nonmetals and other nonmetals, which is one of the ways that they're different than ionic bonds. So we see that the ultimate goal of covalent bonding is the same as ionic bonding, but what happens when we do that is a little different. So I'm going to get out of here for a second. Oh. if my computer lets me. Running slow this morning. Running very slow. So, I'm going to go back here. Myself a blank sheet. Maybe. Okay, so the first thing I'm going to do, I am going to draw myself a Lewis structure for chlorine. And hopefully by now you can do on your own the fact that chlorine is in group 17. It is a halogen. And that means that it has 7 valence electrons. So as we've discussed, chlorine is looking to pick up 1 valence electron to fill the outer shell, its valence shell, with 8 valence electrons. That's how it becomes stable. And if there's an alkali metal around, like let's say sodium, right? We've already established the fact that sodium has this 1 other valence electron. It doesn't want it, so it will transfer it over here to chlorine. Now chlorine has 8 valence electrons. It's happy. Sodium, 8 valence electrons. They're in the previous level. It's happy, but in this process, chlorine has become negative anion. Sodium has become positive cation, and they're attracted to one another, ionic bond. We've discussed that. But let's say there is no sodium around. The only other thing around for chlorine is another chlorine. It's the first thing that that red chlorine atom comes across. So, red chlorine still needs an extra electron. It still needs 8 valence electrons. But is it going to be able to take this extra electron away from the blue chlorine? The answer to that is no. Yeah, red chlorine wants this electron to complete its valence shell, but blue chlorine wants it just as much, maybe even more, because if it loses this one, now it only has 6 valence electrons, and it's even farther away from having 8. This blue chlorine wants an extra electron, but it's not going to take an electron away from this chlorine for the red chlorine for exactly the same reason. So, we have 2 nonmetals, both looking to gain valence electrons. They enter into a mutual agreement. Now, obviously, they can't consciously do this. They're not, thinking beings or anything like that. But due to positive, negative charges, desire to fill that valence shell, energy concerns, what they decide is okay. Oh, I thought these would all stick together. Now they will. What they decide is, all right, red needs an extra electron. Blue needs an extra electron. So they decide that, you know what, we're going to enter into this mutually agreeable situation where we are going to share these 2 valence electrons. They don't belong to me necessarily. They don't belong to you necessarily. They belong to both of us. As a result, right, chlorine, 1, 2, 3, red chlorine, 1, 2, 3, 4, 5, 6, 7 valence electrons. If it counts this blue one that technically belongs to this atom, but is now involved in this sharing, it now has 8 valence electrons. Blue chlorine, 1, 2, 3, 4, 5, 6, 7 valence electrons. If you count this electron right here, which, like again, technically belongs to the red, but now is entered into this sharing situation, it now has 8 as well. So they have this mutually agreeable situation where they both end up with 8 valence electrons. But from a bonding standpoint, remember, there is a positive nucleus inside of this chlorine atom. We don't show it in the Lewis structure, but it's there. And there is a positive nucleus inside this blue chlorine. Now that positive nucleus inside the red chlorine is attracted to this blue electron. Well, guess what? That blue electron belongs to this chlorine atom. The positive nucleus inside the blue chlorine atom is attracted to this red electron that belongs to the red chlorine atom. So now we have the positive part of the red chlorine attracted to the negative part of a blue chlorine. And the positive part of the blue chlorine attracted to the negative part of a red chlorine. Guess what? That is an attractive force. Oh, not what I wanted to do. An attractive force that holds atoms together. That's a chemical bond. So that's how these atoms go about achieving that stable octet, that's 8 valence electrons, and in the process end up being attracted to one another. All right? The sharing of that pair of electrons, one from red, one from blue, has caused them to mutually attract one another. And that's covalent bonding. So, let's get some of the details down here. Covalent bonding. Atoms will share valence electrons so that both will achieve a stable electron configuration. To start off with, we basically say that one electron from one atom and one electron from another atom get shared, and they share 2 of them. That's not always the case. Sometimes one atom will donate both electrons for the 2 to share. It's kind of a rare case. We're not going to talk about it a whole lot in here, but when you get into chemistry, honors chemistry, AP chemistry, be aware that that can happen. As we just discussed, the attraction between the shared electrons and the nucleus of the individual atoms will hold those atoms together. So they still fit that requirement of a chemical bond of there being an attractive force that holds atoms together. We refer to the pair of shared electrons as a single covalent bond. So again, once again, the pair of electrons that are being shared is called a single covalent bond. A single covalent bond is a pair of electrons. So that's the gist of covalent bonding. So let's talk about representing that bond. Here, this is a representing a bond between 2 hydrogen atoms. Up in the top left, that's the electron dot diagram. That's basically what I just drew for you. That's basically what I just drew for you, where we're sharing a pair of electrons, right? In this case, hydrogen, being a small atom, it only needs 2, right? Going back to some of those exceptions. So here we're looking at that pair of shared electrons. A lot of times what you will see is that when we have a pair of electrons being shared, we represent that pair with a single line. We refer to this as a structural formula. That line is representing the pair of shared electrons. So if we go back to my representation of this chlorine, what I could do is this. Here's the red chlorine, Cl, 1, 2, 3, 4, 5, 6. Here's the blue chlorine, 1, 2, 3, 4, 5, 6. But now we replace those 2 electrons in the middle with a single line. That line representing these 2 electrons that are being shared, and a lot of times that's how you'll see covalent bonds being represented. But keep in mind that there are other ways that we can do it, right? The electron dots, that gets to be kind of a pain in the butt if you have to do it a lot. The space-filling model, where we basically fill up the space that represents those atoms there. And then if you go back to like our Schrodinger model of the atom, right, the electron cloud model, you might not show up real well in the projection, but if we show the darker areas representing where electrons are located, the area in between the 2 nuclei is going to be darker than the other areas, because that's where those shared electrons hang out most of the time, right? Darker area, more electron density, a higher probability of finding electrons, because if they're being shared between two atoms, generally they're going to be in the space between them. What we have just done with introducing the idea of covalent bonding, showing you these models here, is we are representing something that we call a molecule. A molecule is an electronically neutral group of atoms held together by one or more covalent bonds. So a molecule is a group of atoms held together by covalent bonds. Here is a electron dot diagram between the molecule formed between hydrogen and chlorine. Here's the pair of shared electrons, the two that they're sharing between them. They are bonded together, held together by a covalent bond. Similar to the chlorine-chlorine that we drew before, except remember, hydrogen only needs two atoms to be happy. So this is a molecule of hydrogen and chlorine. Here's a molecule that you're pretty familiar with, H2O, right? Water. Oxygen's looking to pick up two valence electrons. It's in group 16. It has 6 valence electrons. It needs 2. Hydrogen each donates one of those electrons, and it gets one back. Remember, hydrogen only needs 2 to be happy, and that's a water molecule. Here's another molecule, NH3. Notice, sorry, flipped ahead. All of the elements that show up in these molecules are all non-metal atoms, non-metal elements. Yeah, I know hydrogen shows up way on the other side of the periodic table. It's a non-metal because it doesn't behave like other metal, or it doesn't behave like metals, even though it shows up over on the other side. These are all non-metals. A specific kind of molecule that you've already been introduced to is called a diatomic molecule. Once again, because you know English, you probably could tell me something about diatomic molecules. The fact that the prefix di shows up should tell you 2. The fact that atomic shows up in the name should tell you atom. So it's 2 atoms. But specifically, it's 2 of the same kind of atoms. We've already drawn one diatomic molecule. Chlorine-chlorine, right? There it is. That is a diatomic molecule. It's a molecule because it's a group of atoms held together by a covalent bond, but it's diatomic because it's the same kind. Hopefully, in your head, if you haven't started thinking this already, when I say this I will, if chlorine forms a diatomic molecule, hopefully you're thinking, okay, other kinds of atoms should form diatomic molecules too, like fluorine, bromine, iodine. Why? Because they're all in the same family. If one of them behaves a certain way, all the rest of them in that family should behave that way as well. And what we see is that they do. Also, there are 3 other atoms out there that will form diatomic molecules: oxygen, nitrogen, and hydrogen. Because of that, let's transition out of here and let's go back to my drawing board. So, oxygen, 1, 2, 3, 4, 5, 6. Group 16, 6 valence electrons. Hopefully you've gotten to the point now where automatically you're like, okay, that oxygen has to find 2 more electrons. Well, guess what? There's no calcium around. Calcium's in group 2. It has 2 valence electrons. It would donate those 2 valence electrons to oxygen. It becomes positive. Oxygen becomes negative. Cation, anion, ionic bond. Not the case, though. The only other thing around is this oxygen. 1, 2, 3, 4, 5, 6. Okay, so we've reached an impasse, right? Before, we talked about the idea that chlorine-chlorine, One chlorine isn't going to give up its electron to another chlorine. Same thing with oxygen. They're both non-metal atoms, right? Oxygen and oxygen. They both want to gain electrons just as much as the other one does. So what do? They share. Here, red oxygen, blue oxygen, boom, share. Remember we said that sharing counts for each atom. So now this red oxygen, 1, 2, 3, 4, 5, 6 valence electrons of its own. It's sharing this one. It's only got how many? 7. Is it happy? No. Blue oxygen, 1, 2, 3, 4, 5, 6 of its own. Red oxygen, 7. Is it happy? No. So what happens? Guess what? This one's got another electron just sort of hanging out looking for a partner. This one's got another electron hanging out looking for a partner. Guess what? There we go. So now, how many electrons are being shared? 4 shared electrons. 2 pairs of electrons. If we start counting up valence electrons for the red oxygen, 1, 2, 3, 4, 5, 6 of its own, then it's sharing this one with the blue oxygen. That makes 7. It's also sharing this one with the blue oxygen, and that makes 8. And remember, 8 is our magic number. Blue oxygen, 1, 2, 3, 4, 5, 6 of its own, sharing this red oxygen, or red electron, that makes 7. Sharing this red electron, that makes 8. Everybody's happy. Once again, right? Positive nucleus inside this oxygen now being attracted to these 2 electrons, mutual attraction, chemical bond. Positive nucleus here attracted to these red electrons. Guess what? Mutual attraction, chemical bond. How do we represent that? Well, here's oxygen, 1, 2, 3, 4. Here's blue oxygen, 1, 2, 3, 4. We said that we could use the line to represent a pair of shared electrons. So here's a line connecting these 2 oxygens, but that's not it. They're not only sharing 2 electrons, they're sharing 4 electrons. And that means there's 2 lines there. We refer to this as a double covalent bond, which is a kind of a multiple covalent bond. A situation where, come on, computer. A situation where some atoms are held together by sharing more than 1 pair of electrons. As we just saw, 2 oxygen atoms will share 2 pairs of electrons, or 4 electrons total. We refer to that as a double covalent bond. There are certain instances where some atoms will share 3 pairs of electrons, 6 electrons total. We refer to that as a triple covalent bond. So, just to review, covalent bonding, the end result, the end goal is exactly the same as ionic bonding. 8 valence electrons for all the atoms involved, lower energy. It's just a matter of the way we go about it. Ionic bonds result between a metal and a non-metal because metals are looking to lose, non-metals are looking to gain. Covalent bonds result from sharing electrons coming from, or usually between electrons of 2 different atoms, right? That's going to happen between non-metal and non-metal atoms because they're both looking to gain electrons. So that's all for today. Check the calendar, see if I've updated some of the homework for the weekend. It'll be a real brief introduction review of the covalent bonding stuff, and we'll get back into it on Monday. Have a good weekend, everybody. I'll see you then.